Welcome back. This is the day the Lord's made. Let us rejoice and be glad in it. In this video, I'm going to talk about some DC chemistry topics related to phase diagrams, which would be about how what state of matter substances are based off temperature and pressure. We'll talk about crystal structures, which would be the idea of like how does a molecule pack itself when it forms a solid. We'll talk about coordination numbers, which talk about how many atoms and individual atoms touching around it, how many things are in its general vicinity. We're going to talk about atomic radiuses, so like how big the atom is, using packing structures and crystal structures to do a little bit of math. And we're also going to talk about ionic formulas from a unit cell, so the idea of like how do we figure out the formula if we know what the unit cell is and the packing structure it has. So the first one we're talking about is phase diagrams. All a phase diagram does is show us what state of matter the substance is going to be in, what phase. So here is your generic phase diagram. It's just going to basically say what state of matter am I at, what conditions. So they have a pressure on one axis and a temperature on the other axis, and you can find out what state of matter you are. So this one here looks like it's, I want to say carbon dioxide. But anyway, the general idea is we have a solid when it has what? When there's high pressure, things tend to be solid, or when it's cold. So if we have a low temperature and there's high pressure, it'll be a solid. As we heat it up, we move to the right, the temperature increases, we turn into gases. So over here on the bottom right corner, this would be a very high temperature with a very low pressure. We're going to be a gas. Liquid is this little tiny medium zone where like there's a chance for them to kind of separate. They have enough energy to break apart, but not to become a gas. So almost every single phase diagram looks exactly like this. The only thing that changes really is some critical points on here. All that's going to change is the triple point and the boiling point and the supercritical fluid place. Those would be the basic things that change. So our important locations are triple point. This is where all three phases exist in equilibrium. It's like a fingerprint. The triple point is this place right here in the center of this. It says triple point. That's where a substance can go from a liquid to a solid to a gas and all over, back and forth, and they can all be at equilibrium. All right, it's an important point as far as just identifying the substance. There's another place that's important, and that is the supercritical fluid zone up here. Once you get past this place, I think that's being a box up here. So once you get past this temperature here for the substance and this pressure, so if you're above the high pressure here and above this temperature here and this zone here, you're a supercritical fluid. What that basically means is we can't tell the difference between liquid and gas. They look the same. All right, so basically solids and gas and liquids become the same thing. We call it supercritical fluid because at high pressures, everybody's almost in direct contact with someone else. And so they're behaving like a solid would, having a neighbor, but they're not bound to them because there's so much energy because the temperature is so high. So they are like this liquid that has no intermolecular forces that are actually appreciable and they're just flying around at high speeds. So this is really important. Actually, the most commonly used one is carbon dioxide. It does things like decaffeinate beans. You know, basically you have this gas, the supercritical fluid has a lot of energy and are high pressure, and it can force its way through some material. So you take supercritical fluid, carbon dioxide, and you make it go through some beans. As it goes through the beans, it can dissolve stuff. And so they can dissolve substance out of a solid material. So think of it like a gas, it being such a pressure that can actually just travel right through the substance, and as it travels through the substance, take stuff out. That's pretty much the biggest use of supercritical fluids that I'm aware of. There's probably other ones out there too. We should also note too that this line here between the liquid and the solid, this one here slightly goes to the right for everybody. What that basically means is as we go up this line here, it bends to the right. This is true for everything but water. Water actually goes to the left. So water is a little different in that as the pressure increases, as we go up, it actually opens up to become more of a liquid at higher pressures because water is more dense as a liquid. And so for most things, though, as pressure rises, it turns into a solid. But for water, as pressure rises, it turns into a liquid. So when you're answering questions on the homework assignment, you should be aware that this line here between the solid and liquid bends to the right for everybody but water. So another thing, too, you should be aware of on here, I didn't put it up there, but you should be aware of 1 atmosphere. This is an important place because this is your typical boiling point. At what temperature do you boil? Now, in this case here, we actually go from a gas to a solid here, so it's sublimation at this point, but this is basically standard STP conditions to compare it to, right? So at 1 atmosphere, what state of matter do we expect you to be in? All right, at what temperature? So for carbon dioxide, at 1 atmosphere, we'd expect them at room temperature to be a gas because the room temperature around 20 degrees Celsius. All right. I'm going to go ahead and do a sample question for you guys related to phase diagrams. For these things here, this is a B-level question. It's going to ask you, I think the C ones just ask you to identify the state of matter. The B ones ask you to identify the phase change. So what it's going to do is going to give you some numbers like some temperature and pressure, and it's going to change something and say, hey, we go from this temperature and this pressure to a new temperature. So it is also going to give you what the scale is. So I have it randomly assigning you different atmospheres and temperatures along here. So you just have to like put these things in up there. It's like, oh, A atmospheres is 1.3 atmospheres, B is 5.4, C is 12.1, and then put the temperatures in down here along the bottom. I've already done that for myself. So here are those numbers put in. So here's our phase diagram. All I've done is change the numbers down here. And the question said, what happens when we go from a temperature of negative 196 and 12.1 atmospheres? So I'm going to put down where we start there. Negative 196, 12.1. So negative 196 degrees, 12.1 atmospheres. Here's where we're starting, right here at the S. And we're going to do what? Go back to the question. Says we're going to change temperature to 111.6. So that means we're going to change. We're not changing the pressure, staying at 12.1 atmospheres. But we're increasing the temperature to 111.6. So we started here, ended there. Looks like we're melting. All right. So it's going to ask you what phase change do you expect? So put the numbers in and then find out where you go. See which line you cross. So here we cross solid to liquid. So that's why we're melting. Do take note on these things here. You have negative degrees Celsius. So just be aware, if from negative 39 to negative 20.8, that is getting warmer, even though it's a smaller number, absolute value, it's warmer. So just a quick note. All right, so big idea about phase diagrams. All they do is they show you the state of matter. Everybody looks about like this. All we do is we have these places here where the triple point is, and the temperature for your just normal conditions at 1 atmosphere, your supercritical fluid, these things all change, but they all look pretty much like this. All right, coordination number. This is just a way of saying how many atoms are actually touching the atom, in direct contact with it. So we talk about packing structures, we're talking about how many atoms are in contact with the central atom we're talking about. We've done this before when we did molecular shape. It was pretty much just the X when we talked about this. So again, AX5 would be coordination number 5. We're saying that the central atom has 5 things attached to it. Now we're going to connect this not just to some covalent compounds, but we're going to connect it to like metals packing and ionic stuff packing. That's going to be the difference here, okay? But it's not terribly complicated. So here's a sample question for coordination numbers. Say we have a jar of candy, and we have Snickers bars and Nerds in it. Sounds like a great candy jar to have. So it says every Snickers bar is in contact with 3 other Snickers. And it also says every Snickers bar is in contact with 275 Nerds. What's its coordination number? Oh, well, since every Snickers bar is touching 3 other Snickers and 275 Nerds, its coordination number is just add those together, 278. Its coordination number would be just equal to how many things is it touching. So another question could be, a metal alloy has atoms that have the following pattern. So on the row the metal atom is in, it's in contact with 5 neighboring atoms. On the row above it, it's in contact with 6. And on the row below it, it's in contact with 6. What's its coordination number? So what I mean by in contact, I mean this idea right here. So we can think about the central atom here being in contact with things around it. So in this picture here, I have the metal atom in contact with 6 things here, but in the question it says it's in contact with 5. So just take one of these blue balls out and it'd be touching 5 on the same row. On the row above it, it said it was touching 6 and touching 6 below it. So this picture here, this actually shows the coordination number for the center one at being 12 because it's touching 6 here, 3 on the top, 3 on the bottom. Think about pushing this layer down, putting this layer up. This blue center ball would be touching the 3 above, 6 in the middle, and 3 below. For our question though, it just had 6 above, 6 below, and 5 in the middle. So its coordination number is just 17. So coordination number again, just how many atoms is it touching? So if you get a question related to your molecular shape from before, if I give the notation, hey, the atom has this notation. Again, X is the atoms attached, actually E is the lone pairs. What's coordination number? Oh, X is 2. So that'd be the answer. Moving on. Next thing then would be the unit cell. The unit cell is this idea that we have all these atoms packed together and we can come up with like the repetitive pattern. What is the pattern that forms itself? And so even if you pour a bunch of M&Ms or Skittles into a jar, what seems like randomness isn't really random. There's a pattern to how they pack, how they fit together. So the unit cell just says, what is the smallest repetitive pattern that we have for all these metal atoms that are together? And so there's a variety of them. In this class, we're talking about 3 packing structures, 3 different unit cells. We're gonna have simple cubic, body center cubic, and then face center cubic. So in this class here, we're gonna talk about face center cubic and close packed hexagonal as the same. They're almost the same. As far as we're concerned in this class, they're pretty much identical. The only difference is face center cubic has, I want to say, an ABA pattern, and close packed hexagonal has an ABC pattern, but the actual coordination numbers and number of atoms in the cell for the unit cell don't change. So it's just an orientation thing within the cell. So in this class, we'll keep these guys, we'll count them as the same, but for future chemistry classes, they're not the same with a slight change in orientation. So simple cubic, body center cubic, face center cubic. So in a simple cubic structure, every atom's gonna be touching 6 other atoms. What does that mean? That means that if you think about our simple cubic pattern here, consider this one right here. This one here touches 1 to the left, 1 this way, it'll have 1 to the right, it'll have 1 towards us, and the 1 above and below. It has 4 in the same row it touches, and then 1 below and 1 above. So it touches the 1 top, 1 below, and 4 at every single quadrant around it. That'd be a simple cubic, why it has 6 atoms to touch. Its coordination number is 6. Now the actual unit cell is going to be different. The unit cell is going to be like how many atoms are actually in a single box. So the unit cell will be taking one of these boxes, which would be the smallest thing. How many atoms are inside of this box here? Might have a better picture down here. Yes. So here's a picture of our simple cubic. So a simple cubic, we just have 1 atom at every single corner. So it's just a box. And so at every single corner, every atom that's in there is partially in. How much is in? It's 1/8 in. Because if you think about this atom here, it have like 8 boxes where it's inside of each one of a little bit. So every single corner counts as an 1/8 in. So this atom here is an 1/8 in. This atom's an 1/8 in. This is an 1/8 in, and so on. So inside the unit cell, there's going to be a total of 8 corner atoms, which means that inside the cell there's 1 atom. So in general, simple cubic patterns don't pack very tightly. So you don't get as many atoms into the unit cell. Of course, and usually for simple cubic, we should mention to back it up a little bit. When talking about different packing structures, it comes down to the size of the atoms involved. If it's all the same atom, it doesn't matter. But if it's different size atoms, then you might have different packing structures based off what's most convenient for these atoms to get there. More on that with ionic formulas. All right, the next packing structure is the body center cubic. It looks just like the simple cubic, with the difference that we have a new atom in there. We're going to put an atom all the way in. This atom's going to be directly in the very center. That's a body center cubic when it has a simple cubic shell with an atom inside of it. So just like this one, but the difference is it's got 2 atoms in the cell because the central one is all the way in, and the corner ones are 1/8 in. So 2 atoms, 8 corners, and 1 in. I can have a better picture down here probably. So again, here is our body center cubic structure. There's 8 corner atoms, 1 in the center. So we can see that every single corner atom is an 1/8 in still. Well, compared to last time, they're not actually touching. So on the simple cubic one, the atoms in the corners actually make contact. This will be important for some calculations for those that are doing the A-level stuff. So here they're not touching actually. The middle one actually separates these out just a little bit. So it's not continuous from this atom to that atom there as far as the radius is in contact. The last type of packing structure is face center cubic, which we're gonna, again, if you see hexagonal, closed hexagonal packing, we're gonna call it the same thing. It goes by a lot of different stuff. CCP, SCC, oh man. So there are slight differences between them, but in this class, we're gonna call them all the same, okay? This one here has a coordination number 12. I didn't mention the last one. This one here, coordination number is 8 because every single atom touches 8. So this one was a 6 up here because down here, everybody has 6 in contact. This one here, the central atom is touching 8. So every single corner. So face center cubic has a coordination of 12. Everyone touches 12. And this is going to go by like an rotating structure, what's going on here. It's going to have a coordination number 12 because on the row it's on, it's going to be touching 6, and then above and below it's going to be 3. We had a picture of this before. Let me scroll back up right here. This is an example of the face-centered cubic. So on one row, the central atom is going to be touching 3 above, 3 below, and around it, it'll have 6. So it's just alternating triangles on the top and the bottom. So when it comes to the unit cell, though, we don't draw the unit cell like that because it has to be repetitive in the same pattern. And so the way you draw it is you actually have 8 corner atoms, and then you have atoms on the faces of the square. So think about like a box, and every single edge actually has an atom half in, half out. So we're going to have 6 half atoms in for a total of 4 atoms. So you have the 8 corner atoms still. Each one's going to be 1/8 in. And it's going to have 6 faces on each wall. So let me see if I have a good picture for this one here. Here we go. So the unit cell looks different than the picture I showed you before, but the general idea is instead of having an atom in the very middle, we're going to have 6 atoms on the edges, and then we still have the corner atoms. So for face-centered cubic, we got 8 corner atoms in the cell for the unit cell, and then on every single edge of the box, we're going to put an atom half in, half out. So there's 6 faces on the box, so we have 6 half in, half out. So that makes a total of 4 atoms in there because we have, well, we should mention that we have a total of a distinct 14 different unique atoms. But as far as total atoms inside there, we have 1 atom from the corners, and we have 3 atoms in from the edges ones, which are all half in. So, lots to take in right there. So, in review, simple cubic, this is just box structure, 6 atoms in your coordination number 6, 1 atom inside, all corners. Body-centered cubic, coordination number is 8. Every atom touches 8. And then we're going to have 8 corner atoms plus the middle one. Face-centered cubic, we're going to have a coordination number 12, which means every atom touches 12. It's got 8 corner atoms in the unit cell, 6 half atoms in, so a total of 4 atoms inside the unit cell. This one tends to be the most tightly packed, so it has the least amount of empty space inside of it. All right, now we're talking about some A-level questions. So if you're not going for the A, you can ignore this part. And I think the rest of it's all just A-level stuff too. So you can time out now. For those that are going for the A, so I'm going to do some sample questions about atomic radiuses from packing structures. So how do you find the atomic radius if you know how it packs? So we're going to use the unit cell, the smallest repetitive pattern, to find out what the radius is. So a sample question, I'm going to do one for each one. Simple cubic first. What's the radius of the atom if it has a unit cell edge length of 2.5 angstroms and the simple cubic structure? So what we're saying is the edge length of the unit cell is 2.5 angstroms. So from one corner to the adjacent corner is 2.5 angstroms. What's atomic radius? Well, if you look at the picture of how these things pack, every atom in the corner touches the other atom in the corner. So we have a continuous path that's always touching an atom from one corner to the next corner. So to find the actual radius, we just divide by 2 because from one corner to the next corner that are adjacent, we have 2 radiuses. So 2.5 divided by 2, 1.25 angstroms. That's not too bad, actually. Moving on, the BCC, the body-centered cubic. This one requires a little more math. So we have our edge length given to us, and we want to find the radius of the barium. So this one's a little bit different. Before I go up there and solve it, let me talk it through. So we need to find a place that's continuous, where we always have an atom. It turns out that the continuous place turns out to be from one corner to the back corner. So from corner A, which is going to be the front left corner, to the back right corner is going to be, we can have a continuous path. So this atom in the back right touches the center atom, which touches the bottom left. So we're looking for the diagonal that's going to be going from here to there. All right, so we're starting in the A corner, going to the B corner. We know that we have a continuous path where atoms are touching. And so how far is that in terms of radiuses? Well, A, we have half a radius, we have 1 radius here. So if I'm going from A to touching the center atom, that's 1 radius. Going across the whole sphere is 2 radiuses, and then we have another radius here. So from here to there is 4 radiuses of the atom. All right, here to there, 4 radiuses. So in order to actually figure it out, we got to do some math because we got to figure out how far is it from A to B, knowing that the edge length is 5 angstroms. So we got to do a little Pythagorean theorem, and you'll see that we can make a right triangle. There might be other ways to do it. I just did it using Pythagorean theorem. So I said, okay, well, I found this diagonal down here by saying, well, 5 squared plus 5 squared equals x squared. And this is 7.1 angstroms from here to here across the diagonal. Then I did it again. A squared plus b squared equals c squared. 7.1 squared plus 5 squared equals c squared. And I found this to be 8.7. So here's me walking it through up here. Again, we're saying that we need to make sure the atom's touching everything. We have a continuous radius. We can't just use the edge atoms. You got to go from one corner to the opposite corner. Again, which is that goes through 4 radiuses. So we got to do a little a squared, b squared, c squared. We said our edge length was 5 angstroms. The diagonal 7.1. Then we do it again. Divide by 4 at the end. That would be our angstroms distance for the radius. All right. This is the most complicated one. The FCC one is a little easier. So that's it. Same question, except that I haven't changed the edge length. All I changed is the type of packing, and now we're entering angstroms. Again, we want to find a continuous path. Our continuous path here would be from this corner here to this corner here. So we have an atom at contact because we have these half atoms in, which we actually do have a direct line through all the radiuses. 1 radius plus 2 more radiuses plus another radius makes 4 radiuses. So again, all we're going to look at is from this corner here to this corner here. From corner A to corner B, that is 4 radiuses. So compared to the BCC, we just do a squared plus b squared equals c squared once. So find that that would be 7.1 angstroms, which we knew from before, divide by 4, and that would be the atomic size of that. So quick review. For simple cubic, all you got to do is take the edge length divided by 2. That gets you how big that atom is. For BCC, this will be the one that takes more work. You got to actually find the diagonal going all the way from the front corner to the back corner, completely opposite corners. Find that edge length right there, this distance here, and then divide by 4, because it's 4 radiuses going from this corner to that corner. For FCC, all you got to do is find the distance between one diagonal on one face. So from here to there, that would be 4 radiuses going across there. All right, next thing, we're going to do some sample questions over packing structures. So finding ratios based off of packing structures and how many elements are in different places. So sample question, we have a face-centered cubic structure, and we're told the element X has 6 half faces in, and element Y has 8 corners in. How many X's are in the formula? We just got to find out how many atoms of X and Y are in it, and then we'll know the empirical formula of the structure. So how many X's for how many Y's, given how they pack into the unit cell? For the X's, we have 6 faces. Each face is a half atom in. That means we have 3 atoms total inside of it. For the Y's, 8 corners, each corner is an eighth. That means we have 1 total Y in, which means our formula is X3Y. Quick note when you're doing the homework assignment, sometimes these packing structures don't add up all the way to 4 atoms. Like for face-centered cubic, I might not make it add up to 4. In this case, it did. Sometimes you have holes where like there should be an atom there, but there isn't. So like, and this is actually common for things like when you talk about like doping something, although we don't really make a hole like per se like this, but the general idea is when the atoms pack in, there might be a vacancy. You can think about pouring those M&Ms, and sometimes there's a little spot where there should be an M&M, but it's not there. All right, and there's a vacancy, a hole there. Here's just me drawing that out for you in picture from the last one. We said that the X's had all the face ones, and the Y's had all the corners. So X occupies all these faces. I didn't put the Y's in, but the Y's are all the corners. Each corner is an eighth. So we have 8 1/8, and we have 6 1/2. That's why we have a 3-to-1 ratio. Now the question for us, here we have a simple cubic structure. Element X has 2 corners, Y has 6 corners. We want to know the X's, and we want the empirical formula, which means the simplified ratio. So again, same as before. This time we don't have any faces, so we just have to worry about corners. Each corner is an eighth. So if X occupies 2 corners and Y occupies 6 corners, we can find how many atoms you have total. So it's 2 corners, 1/8 each. That's a fourth of an atom in. 6 corners, 1/8 each. That is 3/4 of an atom inside. The ratio 3 to 1. We'd have 1 X for every 3 Y's. Okay. Ionic stuff is slightly different. All right, ionic stuff, we talk about packing is a little different because what we usually talk about is like the holes that are generated. because the general idea is when a non-metal picks up electrons, it gets bigger, and when a metal loses electrons, it gets tinier. So what we do is we usually talk about ionic stuff being packed as that these anions, which are big atoms, have vacancies around it, and the positive metals, which are tiny, fill in the little vacancy, fill in the little holes. All right, so it might be good to come back and you're just looking at this here, in this packing structure, there's not every single place is filled. So think about the X and the Y being like the anion. The X and the Y are the anion that's taking up the space, and these little vacancies here would be where the positive cations fill in. So you can think of, it doesn't work with table salt. Table salt is simple cubic, but the general idea would be like, hey, if we had Cl occupying the X position and the Y position, the NAs would be actually in these little holes that are between the chlorines. So we're going to basically talk about face center cubic, but it wouldn't matter too much. We're going to talk about these holes, and you can use the holes to find the ratio. So there's different names for the holes based off how the metal atoms actually, or how the anions actually pack. You don't need to know too much how we actually figured it out. You should just be aware that there are 2 tetrahedral holes per anion and 1 octahedral hole. It's a hold. Sorry. So per anion, when we talk about the holes that are around it, like the vacancies, there's going to be 2 tetrahedral holes, 1 octahedral hole. Again, the philosophy, the theory behind it is not too important for this class. You just got to believe that there is a vacancy there. Basically, we're saying up here, we're going to classify some of these holes as different types of holes. So I have a picture down here that talks about that too. Again, inside of a face center cubic, we'd have, so again, think about the red atoms here being like the negatives. They're the anions. They take up a lot of space. There's little vacancies here. Some of these are called octahedral. Right. The octahedral holes are denoted by the O, and the tetrahedral holes are denoted by the T's. So again, you don't have to know what's going on, how they're classified in this class. You just have to know that, hey, per anion, there's 2 tetrahedral holes, which sometimes why it's easier just to, I think of it like this. Per every anion, there's going to be 2 tetrahedral holes and 1 octahedral hole. This is definitely not how it actually packs. It's not how it looks. But as far as like working things out, it's useful. It works just fine. So sample question for packing structures based off of ionic stuff. This is how many oxygens are in the formula for some oxide with cobalt. And we're told that the cobalt atoms occupy 1/8 of the tetrahedral holes and half of the octahedral holes. So we're saying that when we have this, like all these oxygen atoms spread out, we have in some of the holes, some of them are filled, some are not. What that means is some of these holes for the octahedral are filled in, some of the tetrahedral are filled in, but not all of them. So it's not completely filled in. Okay, so the way to figure this out is in order to have 8 tetrahedral holes, because again, we're having 1/8 of them, we have to have 4 anions. Because if you had 4 anions, you'd have 1, 2, 3, 4, 5, 6, 7, 8 tetrahedral holes. And we're told that we have 1/8 of those filled in. So out of those, I just put the tetrahedral holes on the bottom, we have 1 filled in. So I filled it in with a pretty color there. Oh, man. So there we go. 1 filled in. We're told that for the octahedral holes, that we have half of those filled in. So as I've drawn it out, the top ones are octahedrals and half of those are filled in. So what's our formula? We had 4 anions, we had 2 octahedrals filled, and 1 tetrahedral filled. So we have 3 filled out of the total. So we have 3 cobalts for every 4 oxygens. That makes our formula CO3O4. So for these ones, what you want to do is you basically want to, I would just draw a picture, be like, okay, and you can always reduce it down, simplify it. So you could always just probably start with like 4 anions, be like, well, how many are filled in, and proportion it up. So you're basically going to find a ratio between the anions and how many of the holes are filled in to find the actual formula for it. All right, Godspeed.